Let's talk about end behavior. Now, end behavior is actually a very simplistic idea, but it's very powerful in the end result. And it's not hard to remember because we've done the sketches of graphs before, so you've seen the shapes. We're just going to dissect them a little bit. So for instance, if we're looking at f of x equals x squared, what does it look like?
Quadratic.
What's a quadratic? Where does it start?
At 0.
At 0, 0, the origin. And it has a shape which is called a parabola. Now, when we're talking about end behavior, we're not interested about the behavior near the origin. We're actually interested in the behavior of this graph as x goes to negative infinity and as x goes to positive infinity. So basically what you can do is erase the entire middle of this graph and only worry about, well, actually the arrows. So we're really only interested in that this graph is going up on the left and up on the right. That would be its end behavior result. It's going off to infinity on the left and it's going off to positive infinity on the right. We really don't care about what's happening in the middle. We'll determine what happens in the middle in a little bit. All right, so this one I would consider both up. Now if it was negative x squared, they would be both down. Okay, so they go in concert with one another. They're either both up or both down. What about f of x is equal to x cubed? What does that look like?
That's the-
That's that.
Yes.
Yeah.
Now, where does it start? Does it start top left or bottom left? Bottom left. So it's increasing, goes through the origin, and then it keeps on increasing. Not the prettiest picture, but you get the idea. And again, we're not interested in anything happening local to the origin. We're only interested in as it goes to negative infinity on the x-axis, as it goes to positive infinity on the x-axis. So in this case, x cubed is going down on the left, up on the right.
Could never draw these.
Artists. Now, that's normal x cubed, down on the left, up on the right. Now, what if you make it negative x cubed?
What's the opposite?
Does the opposite. So that's all you have to remember about these things. It's squares, both up or both down. Cube is down, up, or up, down. All right, so that would be its end behavior. What do you think happens if I look at f of x equals x to the fourth? Now, we haven't graphed x to the fourth, but you should have some instinct about what it looks like. Do you think it's going to be both up or one down and one up?
Both up.
More likely both up. Why?
Because even number.
It's an even number. When you have an even exponent, that forces all numbers to be
Positive.
positive. So it's going to force all my y values to be positive. The only thing that really changes about the shape is as it gets close to the origin, it gets flatter. It almost becomes boxy looking. So you're going to get a graph that looks something like this. And it goes up a little steeper. But again, I really don't care what's happening at the origin. I care that it's up on the left, up on the right. So it behaves just like x squared. What do you think happens to f of x equals x to the fifth? X to the fifth.
It goes a little slower. Maybe it just gets closer to the x-axis.
It gets a little flatter towards the x-axis. So it has the same shape as x cubed, but as it goes through the origin, it actually is kind of boxy looking. And then when it takes off a lot quicker. Takes off
More of a
It's steep.
more.
Oh, very steep. Just think of it. If you take 2 and cube it, you get 8. If you take 2 and raise it to the 5th power, you get 32.
Okay.
It's 4 times as tall. 4 times
Right.
as quick than
So
raising.
instead of it going off to infinity at a gradual, it's going
Oh, it gets there pretty
to
quick.
shoot straight up.
But it's still kind of shifting to the
Okay.
left, but it's just growing so quickly
I
you
got
don't
you.
see the
Okay.
top. It's like a very tall mountain. This is a
Okay.
little short mountain, a big tall mountain. So the end behavior of the 5th one is also down on the left, up on the right. So what we're going to say is polynomials that have an even degree are going to either be both up or both down. And if they're odd degree, it's going to be one up and
One down.
one down. And opposite orders if you make it negative. All right, so that's just the start.
I'm sorry.
What?
Say that again.
Even, both up or both down. Odd, one down, one up, or one up, one down.
You say in behavior.
You want me to start my whole
I want
sentence
you
over
to
again?
repeat.
You don't have to copy it down. Even, both up, both down.
In behaviors.
I'll type it up for you. Actually, it is typed up for me. It's online.
I can't allow somebody else
See?
to do that for me. Behavior even.
So if we look at something like this, g of x is equal to x minus 3 times x plus 4 times x minus 5. It's a weird polynomial. Before you even start thinking about, we're going to sketch the graph of this thing. Remember what sketch means. You're only going to plot certain points, and then the rest of it is kind of guesswork. So we're going to sketch g of x with intercepts. And of course, end behavior. What is the degree of this polynomial? Because the degree is going to determine whether it's even or if it's odd behavior like. So what is the degree of this polynomial?
Even.
No, what is the specific number value degree of this polynomial? 3. Because if you multiply these three things out together, you're eventually going to end up with the highest degree being x times x times x, which is x cubed. So the degree of this is equal to 3. That's important. I know what the x-intercepts are. I hope you know what the x-intercepts are. You should be able to tell just by looking at this. What are the x-intercepts of g of x? Positive 3, negative 4, and positive 5. So we're going to call these something different. We're going to call these zeros. They're the zeros of g of x. In other words, they're the x-intercepts. But if you're going to say x-intercepts, you have to say 3, 0, negative 4, 0, and 5, 0. If you say zeros, you can leave off the 0 part of it. It's 3, negative 4, 5. The word zeros tells you that y is equal to 0. All right, so I'm going to plot these. Let's see here. I'm not going to be very specific about it. Positive 5 is someplace out here. Let's call that 5. Negative 4 is someplace over here. Negative 4. And 3 is someplace over here. Positive 3. Don't have to be precise. I'm just drawing a little sketch of it. Now, the end behavior of a third degree polynomial is what? Is it both up, both down?
No, it's one up, one down.
Which one's down? Left or right?
Left.
Left. So we know for sure that after it passes negative 4, this thing is going to go down forever. Because it can't come back up, it's not going to hit the x-axis again. And after it goes past positive 5, it's going to go up. So as you move left to right across this graph, you have to kind of go, well, the graph is coming up and it's going to come through negative 4. And then it has to do some funny stuff in between, and then it's eventually going to be taken off to the top right. So all I have to do is figure out the shape of it as it goes through all these points. The other trick is this. If I just graph x minus 3 all by itself, that's the behavior of the graph at x equals 3. If I graph x plus 4 all by itself, that's the behavior at negative 4. And same thing with x minus 5, that would be the behavior at 5. So how do these individual factors behave? What are they called? If I asked you to graph y equals x minus 3, what would this graph look like? Yeah, but what would the graph look like? What kind of shape would it take? Heart attack. If I asked you to graph y equals x minus 3, what would your graph look like? Don't you dare type in the calculator. Oy. Negative 3, 0, sure, I'll give you that. Maybe Kelvin can help us out. Kelvin, how do you graph y equals x minus 3?
Y equals x minus 3. I don't know right now. Give me a second.
Give you a second. It's not horizontal, but it is a
Vertical.
It's a
Line.
It's a line. It has a slope of 1, by the way, because, 1x. That means it's going up 1 over 1, up 1 over 1, up 1 over 1. It's a line. So the behavior at each one of these factors is going to be linear in behavior. So as this graph comes up to -4, the way it has to behave near -4 is a line. So as it comes through -4, it's just going to go through it. Okay. And what happens on a graphing calculator, if you want to look at it, if you zoom up on this, it actually looks like a very straight line. At that one point, a little short segment of it, it looks straight, which is kind of cool if you think about it. So after it passes -4, now it's above the x-axis, but we have a problem. These points are going to draw the graph to it. So I have to kind of take this graph and bring it to
that graph.
that graph. Now polynomials have a nice rolling shape, so don't have jagged zigzags going on here. So you have to kind of roll it through +3. So it's going to roll through +3. And as it goes through +3, it's going to behave like a line, like a straight line. But now it's down below the x-axis, and it's going to get pulled towards the 5. So as it gets pulled towards 5, it has to turn around. And notice it ends up going exactly where I thought it would.
I've seen these things.
So this graph just goes smoothly through those 3 points. And since they're linear factors, it's just going to go straight through them. Sounds easy, right?
Yeah.
Until you leave us alone with them.
Yeah.
Technically, this is like the easiest test question that I have. It's one question. You just draw a little sketch.
You gotta find the degree and the zeros.
The degree, the zeros, and you have to determine what kind of factors you're looking at. These were all
Linear.
linear. So what happens if I have something like this? Oh, it's not that bad. X plus 2 cubed times x minus 1.
So you got 4 degrees.
Its degree is equal to 4. You're going to get 3 from the first one and add on another one that gives you 4.
So it'll be 3
Well-
-2s.
Well, no, you don't think of it that way. It's just at -2, it's going to behave like a cubic.
Okay.
And then this one is linear. So as it goes through 1, it's going to behave like a line. As it goes through -2, it's going to behave like x cubed. It's going to come in and do its little wiggle through the point. All right. So if I graph this thing, oh, there is one thing I forgot about over here. I said intercepts. I only gave you the x-intercepts. What's the y-intercept? How would you find that?
Where it is y.
Yeah, how do you find it? How do you find the y-intercept?
Say that.
Set it to 0.
Set x equal to 0. If you let x equal to 0 in each one of these factors, you get -3 times +4 times -5. You get -3 times +4 times -5, because x is 0. So that would be -12 times -5 is positive. So this point right here has to have 60. It goes up 60. So if you graph this on a graphing calculator, guess what you're not going to see?
Yeah, you wouldn't be able to see that.
On a graphing calculator, this thing looks like this. You have a window, and here's your axis. This thing would look like, see it go through, it would go off the screen.
Yeah, you have
It would hit the y-axis, it would come back down, and then it would go back up, and all you would see is these 3 lines,
Yeah.
which doesn't tell you absolutely anything. So that's why sketching is a little bit better. You get a good idea what the shape looks like of the curve and how it behaves.
So you don't care. Oh, go ahead.
Head on.
You don't care if we put like 1, 2. We can just put like the numbers that we.
Yeah,
get.
if you just put the numbers, I'm happy.
Okay.
I'm looking for how does it go through, end behavior, and the general shape.
You're not going to be concerned about the Y-intercept.
I am.
You want us to indicate
Yeah.
what the Y-intercept is.
Why not? It's easy.
Of course it is.
Well, of course. So when I start graphing this one, just a sketch, I only have 2 x-intercepts or 2 zeros. The 2 zeros are -2 and +1. The cool thing is when you talk about -2, you can say -2 with multiplicity of 3. That's the language that you get with it. It's a 0 with a multiplicity. Where's the multiplicity come from? Kind of like what you were saying, is it -2, -2, -2? So instead of saying -2, -2, -2, you just say -2 with multiplicity of 3. It's a fancy language. All right, so we're going to plot on here, -2, over here someplace. We know that's a 0 of the function. And positive 1 someplace over here. They don't have to be precise, but try to make it look nice. You know, decent spacing. All right, degree 4. What's the end behavior of this thing? Both up. They're both up. It's positive. I didn't make it negative. So it's going to behave like x squared or x to the 4th or x to the 6th. It's going to be both up. So I know as we go to the left of -2, it's just going to go increasing without bound. That's kind of a neat phrase too. And as we go to the right of positive 1, it's going to increase without bound. It's just going to go on up. So as we move left to right, remember that left to right motion I've been trying to get you used to? You really need it here. You have to travel left to right and go through these points the correct way. Now, since -2 is on a cubic, when we get to -2, it has to look like a cube. Probably better yet to make it look like a fifth. Make it really obvious. So instead of coming and directing myself right to -2, I'm going to come in what I call early. So I'm going to aim a little early to -2, and I'm going to flatten this out and go through it. So it has to look like a cube going through -2. So it's not going straight through. You're not driving a straight path. So anything funny done to the factor, you have to come in early and do something. In this case, since it's a cube, you're going to just flatten it out. Now though, after I pass -2, I still have to go through 1, but 1 is linear, so I'm just going to go and aim for it and shoot right through it. So it's going to bend around, you can't do instantaneous rates of change, and go like that. So you get a graph that looks like this, which is kind of cool. What's the y-intercept? How do you find out? Well, you let x equal 0. 0 plus 2 is 2. 2 cubed is 8. X minus, or 0 minus 1 is -1. -1 times 8 is? -8. So it goes down -8. That one would probably show up pretty well on a graphing calculator. Seriously, because all the numbers are within a regular 10 by 10 window. Alright. But I don't like graphing calculators just for the reason that if the picture doesn't show up right, you really don't get a good idea of what it looks like. Plus, you could have typed something, I've done this before, you type something in wrong, the graph comes up really weird looking, and you accept it for the graph. And you typed it in wrong, so therefore, it's graphing something you're not expecting. All right, how about, let's put a lot of junk together. G of x is equal to -x squared times x minus 1 times x plus 3 all cubed.
Ooh.
This has everything.
All cubed?
All, well, the x plus 3 all cubed. The factor x plus 3. Okay, degree?
6.
6. 2 from here, 1 from there, that'll give you 3 plus a 3 more, gives you a degree of 6. Really should have made it odd, but oh well.
Just trying.
The zeros of this function,
Positive 1.
+1,
Negative 3.
-3. Notice I left a space.
Is it positive 1? 0.
0. You have to set each one of the factors equal to 0. X squared is still a factor even though it doesn't have nice parentheses around it. So 0 is also one of the values.
What is the zeros on that one?
The zeros on this one are -2 and +1. The zeros on this one were 3, -4, and +5.
It's -2 and positive.
You set each one of the factors equal to 0 to solve for the zeros. Alright, we can sketch a little graph of this thing. We know the zeros are at 0, literally. +1, -3. So here's -3, of course that's 0, and here's +1. What is the end behavior of this g of x function?
It's going to continuously go up. Or,
Both up?
Yeah, both up. Yeah.
Yeah, both up?
It's got 5.
Oh, it's gonna be down.
It's going to be down because of the negative.
Which negative?
Because if you have an even degree, that forces things to be positive, but because you put a minus in front of it,
You flip.
Okay.
you gotta flip it. So this end behavior is down on the left down on the right. And then you just kind of move your way through this graph piece by piece. Now be careful. This is a perfect square. It has a degree of 2, so it's going to behave like a parabola. This is a perfect cube, so it's going to behave like that little swoosh through the origin. It's going to behave like a perfect cube. And then, of course, x minus 1 is just going to behave like a line and go right through it. So as I come into 3, something funny is happening to the factor. It has a degree of 3. I have to come in early. So don't aim for it. You want to come in early. And it's going to always flatten out when you have something that's not linear. So you're going to get something like this. And it's going to go through in that fashion. It's going to look like a cube. It's going to have that little swish. I call it a flattening. Now, when we get to 0, what kind of thing's going on at 0? Well, 0 is coming from x squared. X squared is going to behave like a parabola. And since it's above the x-axis to begin with, to behave like a parabola, it can't go below. So you're going to come in early, and you're going to bounce off of it. It's going to behave like a parabola. It's going to have that U shape to it. All right, and then we have to kind of turn around and go through 1, but it's just going to go through it. Now notice I didn't end up on my last arrow. That's okay. I just needed that to tell me where I was supposed to end up. Now this one, I already know the Y-intercept. It's right there, it's 0. The interesting thing is, I know nothing about those 2 points. Well, personally, I can find out. You need calculus to find out how tall they go, how high up they go. There is a way of actually finding the maximum values of those 2 bumps.
Well, I'm sure.
Which is kind of,
Well,
I'm sure it's absolutely cool.
oh, it is awesome.
Yeah, we'll do that once we pass this class.
And pre-calculus and calculus.
Yeah, I'm not taking this.
But the idea behind it is actually very similar to a parabola. How
I
you
was going to
find
say,
it.
it was
But it's not a
finding
formula.
the maximum.
You still find maxes and mins of these things.
Right.
Yeah. Which is kind of cool.
In theory, yeah, I get it in theory.
In theory, it's awesome. Everything's not a parabola.
Everything in theory.
In theory. Okay, so that's graphing polynomial equations. What else is there? We talked about zeros. We talked about
Actually,
multiplicity.
I wasn't really looking at the drawing back.
Okay.
So, I understand the contour is going down, but then it just takes squigglies. How does it say you got squigglies? So,
Squigglies. What's squigglies?
I mean, between the -3 and the 1, how do you know that or not? And then,
Because it has to go through -3 and it has to behave like a cube.
okay,
So it's going to go like that.
Okay, I see it.
Once it gets up here, though, you have to turn around and come back towards 0. But at 0, it has to look like a parabola because it's squared. So you're going to come in a little early, bounce off of the 0, and because of that 1, it pulls it back towards it. But it's always pulling it in a nice, smooth, rolling,
So it's a cubic and then parabola.
and then a linear. So cube, parabola, linear.
Okay.
Level, bounce, through.
The 0, where it crosses the origin,
Uh-huh.
wouldn't that for some reason I want to call that it's another parabola, just not pointing down, pointing up.
Yeah, but it's pointing up just because you started in from the top.
What do you?
I call it a bounce, personally.
Oh yeah, I get it. But the bounce so that it doesn't travel through it.
Right, it doesn't go below the x-axis.
Right.
It'll either stay all the way on the top or all the way on the bottom. So even ones will always have this bouncy look to it.
The parabola is the one that says looks like an S, right?
No, that's
No,
cube.
it's cubes.
That's this one. Cube.
Cubic.
Cube, parabola,
I'm trying to like name it on the thing.
cubic, or odd, cube, even, square, and then this one is linear. Linear is odd, but it doesn't behave like the odd cube where it's like that. Yeah, it just goes straight through. It has similar features. Odd will always have one below and one above. One above, one below. Evens will always stay either both on top or both on the bottom. What's the next thing up? Seriously, that's it? This one. You're going to hate this. Intermediate. value theorem.
That's
Excuse me, thank you.
This is the, not the real one. The real one's a little fancier than
we'll
this.
take whatever.
We're going to give you the college algebra version of the intermediate value theorem,
All right.
which is a corollary of the real mean value theorem, which is a corollary of the mean value theorem. Yeah, there's a ton of theorems based on this one. We're just giving you the easy one. So here's the idea behind the mean value theorem. We're going to be looking at an interval on the x-axis. So we're looking at the interval AB, closed interval, closed interval. The second thing that I have to give you is a function, and that it's continuous on this little interval from A to B. Okay. Now this isn't a proof of it, this is just, a mental idea of why things sometimes work. The other condition is this. If I plug in a into f of x, I get this coordinate here. Of course, this coordinate is a f of a. And, there's some graph going through it. I don't know what it looks like. But there's some graph going through that point. And I'm not worried about the graph right now. I'm just worried about the coordinate. And over here is another point. If I plug b into my function, I'm going to get b f of b. And I picked one on the top and one on the bottom for a specific reason. This is the setup of the intermediate value theorem. It doesn't work unless one is high, one is low, and the function is continuous. What's it mean to be continuous? Once you start drawing it, you don't pick up your pencil. There's no gaps, holes, jumps, any weird things like that. Okay, what can you tell me about f of a times f of b? How would you describe f of a in this case? There's only one thing I can describe it. Is it equal to 0?
No.
No,
It's
it's positive. What about f of b?
positive.
It's negative. And if you take a positive times a negative, it's going to be?
Negative.
How do I write that mathematically? Without saying negative. What kind of numbers are negative?
Oh,
No.
no.
Come on, I've taught you this before.
Integer.
What separates positives and negatives?
0.
0. Which way are the negatives?
Okay, then less than
Less than
0.
0. So this means f of a times f of b is negative. I've talked about this before with absolute values and all that fun stuff. So under these conditions, f of x is continuous on AB, and f of a times f of b is a negative value. In other words, one's high and one is low. Then there exists a c, a value c, some real number, on the interval a to b, such that f evaluated at c is equal to 0.
Okay.
Okay. Oh, don't ask any questions yet. Let me go through it piece by piece. Just make sure you got all the little pieces. F of x is continuous. You can't pick up your pencil. You have to draw the curve all the way through. It's on A to B, so it starts at A and it's going to end at B, and I could care less what happens to the left or to the right. It is a function because I wrote it as f of x. And the product of the y values is a negative value, meaning one is high and one is low. Now, the second part of this. When I write C is on the interval A to B, what's the difference between this A to B and this A to B?
That includes in that value.
Right, this one includes the endpoints, this one excludes the endpoints. So this is strictly saying C is between A and B. C is between A and B. So if you want to cross that out and write C is
So
between A
that's
and
what
B.
that little e stands for?
Mhm.
Excludes?
Includes. C is on the interval. C is an element of the interval A to B. It's one of the values between A
You
and
can
B.
use I because it's already, okay.
Yeah, I don't want to use I.
Well, that includes.
This symbol is element. It means element, part of a set. part of a set.
All right.
Such that f of c is equal to 0. What the heck does that mean? If the function is equal to 0, what did I just find?
It's just the midpoint.
Yeah, but if you set a function equal to 0, what are you finding?
But
That's the x value.
What x value?
Let's see.
Yeah, but what is that called? Oh my lord. If I say f of x is equal to 2x minus 3, and I set it equal to 0, what am I finding of the graph?
Oh, wow.
I'm having a hard time putting whatever else you taught us in.
Okay, ready? If I tell you to let x equal 0, what are you finding?
Why?
Y-Intercept.
Intercept.
If I let the whole function equal 0, what am I finding? X-Intercept.
I said X.
You said x.
Alright, okay.
X's, there's how
I got
many
you.
x's
I
are
got
there?
you.
Oh, yeah. Okay.
You gotta understand
So,
what we're talking about.
This one little piece right here is saying C is a 0 of F, or an X-intercept. C is an X-intercept. C is an X-intercept.
Alright.
This is really, really powerful if you think about it. Just by knowing that one point is high and one point is low, I know there's an X-intercept someplace
In between.
in here. Has to be an X-intercept in between. Why? That's the interesting part. Why does it force? Why can't it go, a little bit to the left of A or to a little bit to the right of B? Well, how many curves can I connect these 2 points with?
To be honest,
To be honest,
it's an infinite.
infinite number of possibilities, right? You can have a nice straight line go through them. You can have a wiggly line go through them. And this theorem says all those possible lines have to land between A and B. So here's the reason why. If it doesn't land between, I'm going to be the devil's advocate for a second. If it doesn't land between A and B, it must land on the outside of A and B, like that curve. What's wrong with that green curve? Why does it fail to satisfy all my conditions?
Because it must be up in between.
Now, my conditions are everything before then.
Okay.
So, f is continuous. It's on the interval a to b. It's continuous from here to here. That's fine. And f of a and f of b are products as negative numbers. So one's above and one's below. What's wrong with that green graph, though?
It's not connected.
It's not included.
It's not
What is f?
0.
Why do I put little f's in front of things? What are they called? It's a function. Is that green line a function? Why?
Because the vertical line test.
The vertical line test. If I pass a vertical line through here, how many times do I hit the graph? Twice. The green graph, once I go outside that interval, it becomes not a function. It fails the first thing. It can't be f of x because it's not a function. So it can't land on the outside of a and b because it'll do this vertical line test failing. So it has to land between.
It's pretty.
It has to land someplace between. So the graph has to go between A and B, and it does have to hit the X-intercept, and we're going to call that X-intercept C. Very, very powerful. Forcing an X-intercept between two values that we know is really powerful. Think about that for a second. It's really, really powerful. Let me give you a simplistic example.
When you never mind.
That's the question.
No, wait.
You'll
probably-
wait.
You'll probably answer it in a few minutes.
Find out.
No, actually, what I was going to ask you is when you bracketed the space in between A and B
Uh-huh.
in the graph, the little sketchy thing that you did, no, not that bracket, the other bracket. When you put that green mustache.
Oh,
No, the
What's
mustache.
that?
Get the middle.
Oh, this thing. Yeah.
What was that indicating?
that was indicating this piece right here. C has to fall between A and B. It's the conclusion. But I'm trying to show why the conclusion has to be between A and B because it can't be outside of it. Because once you go outside of it, it's not a function. Yeah. Let me give you a simple example. If I have 2 to the x is equal to 8, what can you tell me? What's that equal to?
3.
3. Automatically you know x is equal to 3. Awesome. Beautiful.
Wow. I looked down for a minute.
Well, I just wrote 2 to the x is equal to 8. X has to equal 3. No algebra went on there, it's just 2 cubed is equal to 8. But the problem comes
alright.
when I write 2 to the x is equal to an easy number, 30. 2 to the x is equal to 30. Now, do you know of any x value that is close to 30?
15.
4. 2 to the 4th is equal to 16. 2 to the 5th is equal to
8.
What? To the what?
oh my lord. 2 to the 4th is 2 times 2 times 2 times 2, which is 4 times 4, which is 16. 2 to the 5th is equal to,
2 times 2 times 2 times 2.
well, 2 times that, which is
32.
32. One of them is too small, the other one is too big. Kind of like this setup, one high, one low. So by the intermediate value theorem, since these two are one high, one low compared to 30, then my answer must lie between,
The two of those.
which numbers? 4 and 5. So x is on the interval somewhere between 4 and 5. This intermediate value theorem is very powerful to finding solutions of things that we don't know how to find solutions of. Now, I could keep guessing. I could probably do 4.5. Use our calculator, get it a little bit closer. And then we would go one high, one low, and maybe 4.75 or 4.25, and one high, one low. That's the intermediate value theorem in practice. Now, how are we going to use it?
Hey, dude, I'm pretty sure we're gonna learn about that element thing or that E.
Oh, will you stop with the symbols? It just means element. It's on the interval. X is on the interval from 4 to 5. X is between 4 and 5. There's a lot of...
We're gonna learn about until the next chapter.
What? No.
Say that?
This is
That's
not.
not the E you're talking about?
This
Oh,
is
God.
E. This is element.
So we haven't learned.
There's more than one E?
There's
Yeah.
one.
By the way, this is such that.
Woohoo.
And for all.
Oh, no, stop.
Mathematicians are amazing.
Remember, mathematicians are
Hieroglyphics.
lazy, so they replace everything with symbols. Okay, how are we going to use it? I need it.
Yeah, so
That's how
we didn't need to write that little example down, did we? Because it's not really what we're using it
At the
as.
Well, actually, we do.
Because
You do it instinctively, for the most part, without even thinking about it. No, not that.
But are you going to show us how we're using it?
Yeah. This is how I'm going to ask it.
Okay.
Example. Given f of x is equal to 2x cubed minus 10x squared minus 51x plus 245. This is one of those ones that my computer generates. Don't let the numbers mess you up because you have a calculator.
now we can use the calculator.
Oh, definitely. And does C exist on the interval 5 to 6 such that f of C is equal to 0? In other words, is there a 0 between x equals 5 and x equals 6? Great. Now be careful with this interval notation. I mean, there's two ways of saying it. You could say C is on 5 to 6, but usually you want to say open intervals, because we don't really want to test 5 and we really don't want to test 6. Okay, so I give you this interval. What does this 5 represent?
5.
Yeah, but what does it represent?
X value.
An x value. So we can rewrite this as x equals 5. What does this 6 represent?
A Y value.
No, it does not.
It doesn't? Another
No,
X value.
because you're on an interval, and intervals are either all x or all
It's another
y.
X value.
It's another x value. So this is x equals 6. Now, just like last chapter, if I tell you what x is equal to, you better go find
Wow.
y. No matter what's going on, go find y and then do something with it. So how do I find y for x equals 5?
Just setting x's to 0.
What?
So you can-
I'm telling you x is equal to 5.
Well, stop.
You gotta put
Put
5
five
in your
in.
phone.
Put 5 in it. You find f of
Fine.
5. So f of 5 is equal to 2 times 5 cubed minus 10 times 5 squared, minus 51 times 5, plus 245. Thank God for calculators.
Really?
You thought you had that before, John?
So, f of 5 is equal to... I'm patient. No. Hurry up.
Negative 10.
Negative 10. Alright, and then you have to turn around and find
6.
f of 6. So f of 6 is equal to 2 times 6 all cubed minus 10 times 6 all squared minus 51 times 6 plus 245, negative 10.
Wow. That's pretty cool.
You should type it in exactly the way it looks, parentheses and
11.
everything.
Yeah,
11. So f of 6 is equal to positive 11. Now, what does that mean? Well, it means the coordinate here is 5, comma, negative 10, and the coordinate here is 6, comma, 11. Does this fit the intermediate value theorem? Number 1, f of x is a function. Is f of x continuous? Well, polynomial functions are all continuous because they have end behavior and they do something in the middle. Does the points go one high and one low? Yes. So therefore, since f of 5 times f of 6 is less than 0, then there is a 0 between, and I'm going to write this really elaborately, x equals 5 and x equals 6. The intermediate value theorem, all the conditions are met, therefore I can say there's a 0 between those two values.
What's the answer?
So what's the answer to this whole problem? This whole thing.
That's it.
That's it.
That's not that
That's the intermediate value theorem. Now, what if you had f of 5 times f of 6 was greater than 0?
It wouldn't be the condition.
It wouldn't meet the conditions, therefore what would you say? There's no zeros?
No,
Or you can't tell?
I don't know yet.
I don't know yet. I like that one better. If they're both positive, think about what happens if 2 points are positive or both of them are negative. It doesn't matter which. There's no guarantee that we have x-intercepts, but there's also no definite not x-intercepts. For instance, let's say my 2 points are up here. Just by having those 2 points up there, does that mean there are no x-intercepts between those two values?
It doesn't say. No.
It doesn't say that. I mean, it could go this way, and stay up above, then there would be no x-intercepts. But it also could do this. And then I would have x-intercepts. So if this condition was positive, then you would just say, can't tell, don't know yet. No evidence to suggest.
Alright.
A lot of different ways of phrasing it. All right, so that's actually a test question.
I don't get it.
Oh, yay.
What don't you get?
I don't know. I understand the plugging in, but I don't understand
Well,
the sense the f of.
This is a negative value, so it's below the x-axis.
Oh.
I don't care about the x, I care
You
about the
get
y. Yeah, and this one is 11, so it's above the. If you have to plot them
You have to have one negative and one positive.
on the y values, on the y values. I could care less about the x. The x is just
So this is
location.
what we're concentrating on, the y value.
And if you have to, draw a little picture. Here is a 5, and here's 6, and this one's negative 10, and this one's positive 11. One's low, one's high. So it has to be an x-intercept between them. Has to be.
So
Now, what if I had a graph that looked like this, and I put a point here, and I put a point here, but I don't tell you anything about f of x, other than it's a graph, it's a function, and those are 2 of its points. Does that guarantee me an x-intercept between them? No. The key word here would be continuous. The key word here would be continuous. Wait, watch. There is a graph that looks like this. And we'll be doing this much later. And it looks like this.
Okay, alright.
And those 2 points would never ever,
Because
have
you
a
did
line
not-
connecting
Because
them.
you did not indicate it was continuous.
Because I did not indicate or did not tell you that it was continuous, there's no guarantee that I can connect these 2 points with a line. Because this graph goes off forever downwards and this one goes forever upwards. And they never ever touch, which is kind of cool. That was a trick question on a calculus exam. I said it did. I was an idiot. I didn't read all the conditions.
But you knew the answer.
I knew it. I knew the answer if I thought about it, but I didn't think about it. And that's the danger with math. If you just assume things are true, you're going to get kicked a few times. Okay, so that's intermediate value there.
The only way.
Yeah. Next topic.
Topic?
3. Yeah, we have time.
I
That's
know.
not what I'm saying.
Yeah, we do.
I know.